welcome back. We're going to look at a new topic today, and the introduction of this topic was the last couple of chapters, right? In the last two chapters, we learned about energy as it's related to chemical reactions, and so we figured out how to determine the amount of energy that a chemical reaction releases or absorbs, what its effect is on its surroundings. The last chapter, we learned how to determine whether or not a chemical reaction would be spontaneous when we figured out the Gibbs free energy. If it was negative, remember the reaction would be spontaneous. In other words, once you hit the activation energy for that chemical reaction, it would continue. But I want you to consider a couple of reactions as we get into our topic for today. The first is the combustion of ethanol. So here's the reaction for that. As the ethanol is combined together with the oxygen, produces carbon dioxide and water. That's the first reaction. The second reaction is the rusting of iron. And so here we have solid iron combined together with oxygen and produces the rust. And so the question is, well, obviously these are both spontaneous because those are reactions that happen easily. They're spontaneous at room temperature. So we would expect if we calculated the change in G that they would both be negative, and sure enough they are. But what we might think, because this one, you've got flame and you've got heat. If we compared the energy released by the two of these, we would probably expect that this produces significantly more energy than this reaction does. If we calculated the change in H, the change in enthalpy of the two, we would expect change in H to be much higher for this one than it is, or much greater than for this one than it is for the other, than for the second. And we'd actually be wrong. This is a little bit greater, but it's not significantly greater. And so, as it turns out, this reaction here, it produces enough energy for us to, for example, boil water. You could never boil water, though, with the energy produced by this. Well, if the energy produced, if the change in energy for the entire reaction is very close, then why can we boil water with the first and not boil water with the second? And the answer to that question is kinetics. Kinetics is the study of chemical reaction rates. And so that's what we're going to look at this chapter, is the rate of a chemical reaction. The reason this one can boil water is because it's a reaction that occurs very quickly. In a very short period of time, it releases that energy. This one, however, even though it releases nearly the same amount of energy, that happens over a long period of time. So that's why you can't actually boil water with that. So I want to give you an equation for the reaction rate. And it has to do with the concentration of the chemicals that are in a reaction. If you have a reaction that's in this form, A plus B yields C plus D, right? Substance A plus substance B, those are the reactants. It will give you the product C plus D. Then the rate of the reaction is going to be equal to the change in the concentration of C. Remember, the square brackets mean the concentration of a substance. The change in the concentration of C over the change in time. Now I picked C. I could have picked D. This is the rate equation for products. Okay. And if you do the rate equation for a reactant, it's very similar. Let's pick A. It's going to be negative change in the concentration of A over change in T. And the reason why is because for a reaction, obviously the concentration of the reactants is going to go down over time because the reactants are being used up. So we put this negative sign here in front of it if it's a reactant, so that our overall rate will always be a positive number. Okay? So I just want to do a quick example. There's actually not one in the book, so I just made one up. Using these, I forgot right now, this is for reactants, right? For reactants. So this one's for products, this one's for reactants. Okay, so let's just do a quick example. Let's say that we know for a particular reaction that a substance, some substance, we'll just call it substance A. Substance A has a molarity. Remember, molarity has to do with the concentration. So molarity M for this substance, M equals 1.30 molarity at 2 seconds. So 2 seconds into the reaction, right? That's the molarity of substance A. And then the molarity, if we check it again at 10 seconds, right? At 10 seconds, we find the molarity, the concentration of the substance to be 1.02 molarity. And so the question is, what is the reaction rate for this particular reaction? And is substance A a reactant, or is it a product? Okay. So the second question is actually the easiest one to answer, right? Because the concentration goes down over time. This number is smaller than this number. And so that means that this has got to be a reactant. So we know it's a reactant. As far as calculating the reaction rate, now that we know that it's a reactant, we know which equation we're going to use. We're going to use the equation negative change in the concentration of A over change in T. Right? And so we say then that, well, I actually have a chair I can use. Nice. The concentration of the negative of the concentration of the change in A is going to be the final value of its concentration, 1.02 molarity, minus the original value, 1.30 molarity. All of that over 10 seconds minus 2 seconds, right? That'll give us the change in time. And so we punch that in our calculator and we get a value of 0.035 molarity over S. That's our unit there. All right? So that's how we determine the reaction rate if we know the concentration of a particular substance in the reaction at one point in time and another point in time.